Imagine absolute nothingness. No light, no sound, no space, no time, just an endless void, empty of all existence. And then something happens. A moment so powerful, so incomprehensible, that it brings an entire universe into being. The Big Bang, the beginning of everything we've ever known. But what really happened at the very first instant of time? What sparked the birth of our universe? And could something have existed before it? These are some of the biggest, most mind-bending questions in all of science, and today we're diving straight into the cosmic unknown. We'll explore what we know, what we don't, and the mind-blowing theories that could change everything we think we understand about the origin of reality itself. Because the story of the Big Bang isn't just about the past, it's about us here and now, and the forces that continue shaping our universe today. But before we journey back to the dawn of time, let's take a moment to build something incredible together. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Now, let's begin. The Big Bang Theory is one of the most well-tested and widely accepted models in modern cosmology. But contrary to what many people imagine, the Big Bang wasn't an explosion in space. It was an expansion of space itself. There was no empty void waiting to be filled. Space and time were created in that very moment. It wasn't just a burst of energy either. It was the beginning of all physical laws, the foundation of everything from gravity to electromagnetism. But how did we even come to this conclusion? For most of human history, we believed the universe was eternal, unchanging, infinite, always existing. Ancient civilizations saw the stars as permanent fixtures, gods painted onto the cosmic canvas. Even in the early 20th century, many leading scientists, including Albert Einstein, clung to the idea of a static universe. Einstein's general theory of relativity, published in 1915, predicted that space itself should be either expanding or contracting. But this idea was so unsettling that he modified his own equations, introducing a mathematical fix called the E, cosmological constant, designed to keep the universe frozen in place. But nature refused to stay still. In 1929, astronomer Edwin Hubble made a discovery that shattered our understanding of the cosmos. Observing distant galaxies through the massive Hooker telescope, he found that their light was shifted toward the red end of the spectrum, a phenomenon known as redshift. And the farther away the galaxy was, the more extreme the shift. This was undeniable evidence that galaxies weren't motionless, they were rushing away from us. The universe itself was expanding. This single realization led to an astonishing conclusion. If the universe is expanding now, then logically, if we wind time backward, it must have once been much smaller. Imagine shrinking everything, every galaxy, every star, every atom, into a single point, a singularity, a place of infinite density, infinite temperature, where all the matter and energy of the universe was compressed into something smaller than a subatomic particle. This is what scientists believe the universe was like at its very first moment. But this idea didn't emerge overnight. In fact, it was a Catholic priest and physicist, Georges Lemaitre, who first proposed it in 1927, calling it the cosmic egg, a primordial atom that suddenly expanded, giving birth to the cosmos. At first, many dismissed his idea, even calling it religiously motivated. But as evidence mounted, it became clear. Lemaitre had been right all along. Still, the name Big Bang was never meant to describe the event accurately. In fact, it was a joke. In the 1940s, British astronomer Fred Hoyle, who didn't believe in the idea at all, mockingly referred to it as this Big Bang during a radio interview. Ironically, the name stuck, and now it defines one of the greatest scientific revelations of all time. But here's where things get truly bizarre. The Big Bang Theory describes what happened after the universe began, but it doesn't explain what caused it. And when we try to mathematically describe that first moment, everything breaks down. Gravity, quantum mechanics, the laws of physics, as we know them, none of them seem to work in this extreme environment. Something deeper is at play, something we still don't fully understand. So what actually happened at the very first moment of time? And is there a way to peer beyond the veil to glimpse what came before? The moment the Big Bang began, the universe was anything but recognizable. There were no galaxies, no stars, no atoms even, just a blinding storm of pure energy compressed into a singularity so small that it defies imagination. And then, in less than a trillionth of a second, reality itself transformed. Space expanded at an almost incomprehensible rate. Temperatures dropped, and the fundamental forces of nature took shape. But what exactly happened in those first moments? And can we ever know what came before? To answer that, we have to go back to the very first instant of existence, a time so extreme that our current understanding of physics collapses into chaos. This is the Planck epoch, a moment so brief that it lasted only 10 to 43 seconds. That's an unimaginably tiny fraction of time, a decimal point followed by 42 zeros and then a 1. This is the smallest unit of time that makes physical sense, beyond which all our equations break down. At this point, everything in the universe, the entirety of space, time, matter, and energy, was crammed into an infinitely dense, incredibly hot singularity. The temperature, a staggering 100 million trillion degrees. That's so hot that even subatomic particles couldn't exist. In this state, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single, mysterious superforce. But something happened next that would set the course of the entire universe. In an instant, this singularity didn't explode. It expanded. Space itself ballooned outward in what scientists call cosmic inflation. Imagine taking a microscopic point and stretching it to the size of a galaxy in a fraction of a second. That's how fast inflation occurred. This idea was first proposed in 1981 by physicist Alan Guth, who realized that such an event could solve several cosmic mysteries. One of them is known as the horizon problem, the question of why opposite sides of the universe, separated by billions of light years, look almost identical in temperature and structure. Normally, light would need time to carry information between these regions, but there simply hasn't been enough time for that to happen. Inflation solves this by proposing that all these regions were once in close contact before being rapidly stretched apart, ensuring uniformity. But inflation also introduces another strange consequence, one that might explain why our universe exists at all. During this rapid expansion, quantum fluctuations, tiny random energy variations at the smallest scales, were stretched across the cosmos. These fluctuations later became the seeds of all structure in the universe. The galaxies, stars, planets, even us, owe our existence to these microscopic ripples in the early fabric of space. If inflation hadn't happened exactly the way it did, our universe might have remained an empty, featureless void. But here's where things get even stranger. Inflation, if true, suggests that our universe may not be alone. According to some versions of inflation theory, different regions of space could continue inflating independently, creating a vast multiverse with countless universes, each with their own laws of physics. Some could be completely alien to our own, places where gravity is stronger, where atoms never formed, or where time itself flows in ways we can't comprehend. But let's come back to our own universe. Inflation didn't last long, just a fraction of a second, and when it ended, the universe was still nothing like what we see today. It was a cosmic fireball, filled with a thick plasma of fundamental particles, quarks, electrons, and neutrinos, moving chaotically in all directions. As the universe cooled, something miraculous happened. Quarks, which had previously existed, in isolation, began to stick together, forming the first protons and neutrons. This was the birth of atomic nuclei, the building blocks of all matter. But at this stage, the universe was still too hot for actual atoms to form. Any electron that got close to a nucleus was instantly ripped away by the intense energy surrounding it. For hundreds of thousands of years, this chaotic, searing plasma filled the universe, preventing light from traveling freely. And then, at a critical moment, The universe underwent another transformation, one that would allow light to finally break free. What happened next? And how did this chaotic, fiery state evolve into the breathtaking cosmos we see today? The universe was still young, just 380,000 years old, but it had already transformed dramatically. What was once an unimaginably hot and dense fireball had now expanded and cooled to about 5,400 degrees Fahrenheit. Still scorching by any human standard, but finally low enough for something remarkable to happen. For the first time, electrons, those tiny, restless particles that had been zipping chaotically through the plasma, were able to slow down and settle into stable orbits around nuclei. This was the moment atoms were born. Hydrogen and helium, the simplest and most abundant elements in the cosmos, finally took shape. And with that, the universe became transparent. Before this, the searing plasma had acted like a cosmic fog, constantly scattering light. But now, for the first time, photons, particles of light, were free to travel across space. This event is known as recombination, and the light released in that moment still surrounds us today. We see it as the cosmic microwave background radiation, a faint glow stretching across the universe, carrying an imprint of the Big Bang itself. Discovered by accident in 1964 by Arno Penzias and Robert Wilson, this radiation is one of the strongest pieces of evidence for the Big Bang theory. When the two scientists first detected it, they thought it was a mistake, some kind of interference, maybe even pigeon droppings on their equipment. But no matter where they pointed their antenna, the signal remained the same. What they had stumbled upon was a snapshot of the infant universe, frozen in time from nearly 14 billion years ago. But if you had been floating in space back then, an impossible thought, given that nothing solid existed yet, you wouldn't have seen a universe bursting with stars. You would have seen darkness. The birth of atoms had allowed light to escape, but there were no sources of new light. The universe had entered its cosmic dark ages, a vast, featureless expanse with no stars, no galaxies, just an ocean of gas, stretching in all directions. Yet hidden in that darkness, something incredible was beginning to take shape. Even though the universe looked empty, it wasn't. Tiny variations in the density of matter, those quantum fluctuations stretched out, by inflation, meant that some regions contained slightly more hydrogen and helium than others. Over millions of years, gravity started to pull these denser regions together, slowly forming massive clouds of gas. The more mass these clouds gathered, the stronger their gravity became, pulling in even more material. And then, the first stars were born. Deep within these collapsing clouds, pressure and temperature skyrocketed until nuclear fusion ignited, a process where hydrogen atoms fused together to form helium, releasing an immense amount of energy. This was the first time since the Big Bang that light had shone anew. These weren't stars like our sun. They were monsters, gigantic, unstable, burning at extreme temperatures and living fast, furious lives. Some of them were hundreds of times more massive than the sun, shining with a brilliance that would have made modern stars look dim by comparison. These were the population 3 stars, the very first generation of stars, and they were responsible for shaping the universe as we know it, because these ancient stars weren't just cosmic light bulbs. They were factories, forging new elements deep within their fiery cores. The Big Bang had only produced hydrogen, helium, and a tiny trace of lithium, but nothing more. Yet inside these stars, nuclear reactions churned out heavier elements. Carbon, oxygen, nitrogen, even iron, the very materials needed to create planets and eventually life itself. But these first stars were also doomed. They burned through their fuel rapidly, living only a few million years before meeting catastrophic ends. Many of them exploded as supernovae, unleashing titanic amounts of energy and scattering newly forged elements into space. Others may have collapsed directly into black holes, seeding the cosmos with the first gravitational monsters. These violent deaths triggered the next great chapter of cosmic evolution. The ejected material from these explosions enriched the surrounding gas clouds, making it possible for the next generation of stars to form. And this time, something different happened. Stars began clustering together, forming the first galaxies. The universe, once dark and empty, was now teeming with light. Vast swirling structures emerged, proto-galaxies merging, colliding, shaping the grand cosmic architecture we see today. But how did these early galaxies evolve into the breathtaking spiral and elliptical galaxies that fill the cosmos now? And what role did mysterious dark matter play in sculpting the grand cosmic web? The universe had transformed. What was once an empty, dark expanse had become a dazzling spectacle of light, galaxies stretching across space, each filled with billions of stars. But these early galaxies were chaotic, turbulent battlegrounds, constantly colliding and merging, shaping the structure of the cosmos itself. And yet, hidden beneath all this brilliant activity, there was something else, something unseen, but fundamental: dark matter. Even though it's invisible, dark matter's presence was inescapable. As galaxies formed, they weren't simply scattered randomly across space. Instead, they arranged themselves in vast interconnected filaments, a cosmic web stretching for billions of light years. At the intersections of these filaments, galaxies clustered together, forming the enormous superstructures we see today. But what was holding this web together? The gravity of normal matter alone wasn't enough. Scientists realized that something invisible was acting behind the scenes, shaping the very fabric of cosmic evolution. This mysterious substance, dark matter, doesn't emit light, doesn't interact with normal atoms, yet it accounts for 5 times more mass than all the visible matter in the universe combined. We still don't know what dark matter is, but we can see what it does. It acts like a cosmic glue, helping galaxies stay intact and influencing their formation over billions of years. Without it, the universe might look very different. Galaxies might never have had the mass needed to hold together, and the grand structures we see today might never have formed. And so, as time passed, these galaxies grew and evolved, their stars continuously being born and dying in an endless cycle. But among them, something special was about to happen. In a relatively unremarkable corner of the cosmos, inside a galaxy we now call the Milky Way, a swirling cloud of gas and dust began to collapse. At its center, pressure and temperature soared, and nuclear fusion ignited. A new star was born. A rather ordinary star, but one that would one day become the heart of something extraordinary: our Sun. Around it, remnants of the gas cloud clumped together, forming planets, asteroids, and moons. Among them was a small, rocky world, bathed in just the right amount of warmth. Over millions of years, that world transformed, oceans formed, atmospheres thickened, and then, somehow, against all odds, life emerged. Think about that for a moment. The same forces that shaped galaxies also led to you, sitting here right now watching this video. Every atom in your body, your bones, your blood, your very breath, was once forged in the heart of an ancient star that lived and died long before Earth even existed. This is the legacy of the Big Bang, a chain of events stretching across nearly 14 billion years, leading from an unimaginable singularity to the vast living universe we see today. But what happens next? The universe is still expanding, its galaxies drifting ever farther apart. Will this expansion continue forever, until everything is too far away to see? Will dark energy, another mysterious force, one day rip the cosmos apart? Or will gravity eventually pull everything back together in a final catastrophic collapse? A big crunch? We don't know. Not yet. But what we do know is that we are part of this story, a momentary flicker in the vast cosmic timeline, yet profoundly connected to the universe itself. And so, as we gaze up at the night sky, we aren't just looking at stars. We're looking back in time, back to the origins of everything. But now I want to hear from you. What do you think the ultimate fate of the universe will be? Will it expand forever, collapse, or something else entirely? Let me know in the comments below. And if you enjoyed this journey through time and space, don't forget to like this video, share it with other curious minds, and let's keep unraveling the mysteries of the universe together. Because the story of the cosmos isn't over yet. It's still being written.